the first thing that I want to talk about, when we deal with transformations, what are some of the types of transformations you can recall? Anybody, can you tell me a transformation that you recall? So when we talk about transformation, we talk geometric transformations, not glow ups. Tell me, what transformation do you recall? Lovely. A translation. A translation is probably one of our simplest of transformations, which back in the day when you first would have met it in primary school, you would have learned about the slide. Alright? The slide. So, a translation. Alright? Let's just say, for example, let me see if I could construct a little shape for the while. Alright, nice. So, let's say we had this triangle. Alright, vertices A, B, and C. A translation would mean that I can slide this triangle absolutely anywhere in my Cartesian plane. So I could slide my triangle along the x-axis, along the y-axis, and I could do movement in either of these directions. So this movement is two-dimensional, right? It's two-dimensional. And can anybody tell me if they recall working with a translation vector? Anybody recalls working with a translation vector? So I hear nothing at all. No one recalls working with a translation vector to represent the translation of the shape in the coordinate plane, or you might remember it if you see it. Was that Julie's? Just now. The message didn't pop up. Okay, so Julie says yes. Alright, so when we deal with translations, we could say things like, well, you move in the x direction and y direction by a certain amount of units. Now, your translation could be easily represented as a translation vector. And we're accustomed to vectors, we've seen vectors, we know vectors, right? Vectors are those column matrices, right? 2 rows, 1 column. We use this to represent our translation. And what we put in our translation vector would be the information for the movement in the x direction and the movement in the y direction. So when we deal with a translation, let's say the movement that I have on this particular triangle, right? So I translate triangle ABC, and it gives me this new triangle A prime, B prime, C prime. Alright? So if I wanted to get a translation vector for the translation which occurred to take ABC to A prime, B prime, C prime, can anybody recall how you would obtain the information for the translation? Right. Alright, so that's one suggestion. So we're going to take a look at the original coordinates. So we're looking at triangle ABC. We're taking the coordinate of one of those original points, and the second part, I think she sort of trailed off a little bit, but she was talking about using the translation vector information and the transform coordinate. So what I'm actually trying to get now, right? So if you're looking at the chat, you all will see Jaleese mentioned a plus t is equal to a prime. Alright, now that particular equation that she has there, that is to obtain the translated point. Alright, that's to get the coordinates of the translated point. What I'm asking is, how am I getting the information about the translation itself? The translation itself, not the transformed coordinate. But if I ask you all, well, describe for me the translation which took place here. Can you do that for me? Can anybody do that? Describe the translation which took place. Exactly. So, like she just said, we could fill in the such and such with some values in a little bit. Alright, that's why I kind of take my time on labeling this out. But she's on point with it. When I ask you to explain to me or to describe or to give me the information about a translation, I'm asking you, how many positions in the x direction or the y direction did this particular shape move? And that's where you're going to get the information about your translation, right? So if you're able to read your Cartesian plane properly, right, and you know how to state movement in the Cartesian plane properly, you'll be able to tell me how many places did this particular triangle move in both the x and y direction. Now, obviously, you might look at it and yes, I have arrows, but that was just to demonstrate the movement, right? But if I want to get the translation vector, or I want to at least get the information for the translation to explain it in words like she did just now, I am going to take a look at one of the original coordinates. So exactly what Calissa started off by telling us here, right? The original triangle, we're going to look at one of the points coordinates. So if we look at A is the point 1, 1. And for me to be able to figure out how many spaces this triangle is translated left, right, up, down, I need to first look at the transformed coordinate of A. So the transformed coordinate of A is A prime. Alright, so I'll just see if I could get all the way down here quickly. Right? So take a look at it now. You're comparing the original coordinate of A, which is 1, 1, with the transformed coordinate A prime, which is at 8 minus 7. Okay? 8 minus 7. So these are your coordinates. So we have A is 1, 1. And A prime is 8 minus 7. So if I want to get the translation information, what am I going to do? Alright, so there are a couple of ways you could do this. One is the very simple way that you probably would have been accustomed to way back. You're going to count the number of spaces you move to the right in this case, because our triangle is being translated to the right along the x-axis, and then count the number of spaces you translate downwards. So let's start at 1, 1. Right, we're starting at 1, 1, and we're moving to the right by a total of 7 spaces to get to 8. Alright, because the x-coordinate of the point A prime is 8. So we've moved 7 spaces to the right. So I'm going to just write that down. 7 spaces to the right. And now we're going to talk about how many spaces we move downward. So we are at 1 again, and we're counting how many spaces we move downward. So we move downward by a total of 1, 2, 3, 4, 5, 6, 7, and 8. A total of 8 spaces downward to get to minus 7. So very simple way of getting your translation. You count the spaces that you move from one point to another. Now that only works for a transformation, obviously, like a translation. Alright? There are other transformations that would not work so simply, so we'll discuss those in a bit. But with the translation, there's a very simple way in which we can I nearly put 2 8 spaces downward. Alright, yeah, but that's the one thing with translations that you would definitely appreciate, right? It's pretty simple. You can count how many spaces you move in any direction, right? Because it's a 2-dimensional movement. Now, if I want to write a translation vector, I'm going to combine this information that I have and put it into a translation vector. And the translation vector T would be 7, yeah, if it isn't 8 to the right and 7 down, no, it wouldn't be, because you're comparing the location of the point A and A prime. So maybe when I show you the other way in which you could get your translation vector from using the coordinates of the points, it might make a little more sense, and it wouldn't be so confusing, because I see you, Masha, no problem. Alright, so Masha, if you're now joining us, don't worry, we're just right here talking about translation vectors. We were going over some of the basic things that you would have covered back in lower school, and even for some of us, we might remember doing translations way back in primary school when you called it a slide. So we slide to the right. What was the name of that song again? Is Electric Slide? Yes, Electric Slide. Anyway, so yeah, slide to the right, a total of 7 spaces. And when I talk about moving 7 spaces to the right, it's because my point A is at 1, right? It's at 1 on the x-axis. And then A prime is on 8 on the x-axis. So this is how I can tell it's 7 spaces to the right that I'm moving. Alright? And then I have to count how many spaces I move downward. And if you'll pay attention to the translation vector here, because my movement is downward, this is the reason why I'm going to use a negative 8. So it's not going to be positive, because positive would indicate that we moved upwards. So the signs are very important with our translation vector. Depending on the direction we move in, that is going to determine the sign of the numerical value that we have for our movement in the x direction or the y direction. Alright, now I mentioned that you can get your translation vector using the coordinates in a different way, and this way is a method that involves understanding our algebra with matrices, with vectors, because vectors being a subgroup of matrices, we needed to understand how we do our operations with matrices first and foremost. Now, how am I going to even do that? Alright, so you're probably looking at it and you're saying, oh, this is a translation vector, but these guys are coordinates. Anytime you have coordinates, you can represent a coordinate as a vector. True or false? Anytime you have the coordinates of a point, you can represent it as a vector. Is that true or is that false? It's true, because if you'll remember, when we were dealing with vectors, you all would have seen that there were some problems where the position vector was basically the coordinates of a point, right? And we just take the coordinates at that point and just write it in a vector form. So can you all write A and A prime as vectors for me? I want to get my translation vector. So if I want to figure out, well, okay, what took me from A to A prime, this is what I'm going to do, okay? Because I end up at A prime, this is the vector that I will start with, right? So I'll put 8 minus 7. And you might be able to even reconnect this with like your triangle law of vector addition and whatnot. If not, um, you know, it's not mandatory that you have to reconnect it to that, but it just might make more sense, right? The vector technique will make a little bit more sense as well. Now, I want to get the translation vector, right? So I'm going to subtract the vector for A. And when I work this out, once my basic arithmetic is good, I'll get my translation vector. Alright, so 8 minus 1 will give me positive 7. And then minus 7 minus 1 will give me minus 8. Alright, so as I was saying, if we wanted to use a vector approach, this is what you do. You subtract the vectors of the transformed points and the original points, and that will give you a translation vector. And if you look at it, the translation from A to A prime, right? This blue line is terribly not straight as it is. You could construct a triangle from A to A prime. And that's why I said you can connect this particular thing to your triangle law of vector addition, right? Which would obviously result in a subtraction because you want to get a translation vector. But this is how you would do the matrix approach then to getting your translation vector if you were asked to get a translation vector. Alright? So this was just to go over the translation in the Cartesian plane and to identify the way in which you get your translation vector. Alright? So anything anybody wants cleared up before we continue, like there's any question that you have, ask it now. So they could give you a question like this with translations in multiple ways. They could give you the Cartesian plane with the shape and the transform shape, ask you to find translation vector. They could probably even give you it in a worded form where they tell you that a shape is undergoing a translation, and they will give you the transform coordinates and they will ask you to find the translation vector. Or they could give you the translation vector and ask you to transform the original coordinates of the shape and get those transformed points. So there are a couple different ways you could get it, but with translations tend to be a lot more simple, or well, a lot simpler. Bad superlatives. Yeah. Translations tend to be a lot simpler when you get this type of question in your transformations and merging with matrices, right? That question 10. Translations, they tend to be a lot easier. Then they have a tendency to like to bring reflections, rotations. So we'll talk about those shortly. And enlargements and dilations. Those actually involve matrices, right? Now, the movement for translation is really, really simple. And you could do that like I was showing you all, counting. You don't need to stress. And you could also connect it with your vector knowledge. The one that involves the matrices, the ones that, like I said, the rotations and the reflections, those in particular, there are specific matrices that you will have to learn off to be able to like use them. And those might not be as straightforward as these are. But the important thing that you need to be able to remember here when you see this particular type of question, a transformation question in the matrices question on a test paper, you need to remember your arithmetic operations with the things like vectors and matrices. So for translations, it most times would be like addition and subtraction. But for your reflections, rotations, enlargements, dilations, those would be matrix multiplication. So that's I guess you could say the kind of key thing with these types of questions, just knowing which operation you have to perform. So when we get to the reflections and rotations and stuff, um, you'll see those questions, they tend to come in the same way. They could give you a diagram and they will tell you, well, what is the transformation what is the transformation taking place, and give a matrix to represent the transformation and whatnot. So we'll talk about that in a little bit, but this is what translations could look like. And I do have a past paper question that we could look at with translations in a short bit. But any other questions pertaining to like getting the translation vector, the coordinates as a vector thing? No questions there, everybody? It makes sense to them? Okay, it makes sense. Alrighty, so let me clear this off now.